May 14, 1917. Aberdeen Proving Ground, Maryland. Major General William Crozier, Chief of Ordnance for the United States Army, held a British Mills bomb in his right hand and an American-manufactured copy in his left. The two grenades looked nearly identical, same distinctive pineapple shape, same segmented cast-iron body, same 4-second fuse, same basic design. But they weren't identical where it mattered. The British grenade in Crozier's right hand had been tested in 2 years of trench warfare. It had killed thousands of German soldiers. British troops trusted it completely. The American copy in his left hand had never been in combat. It incorporated what American ordnance engineers considered improvements over the British design: more precise manufacturing, better quality control, refined detonator mechanisms. Captain James Parker, the ordnance officer supervising American grenade production, stood beside Crozier, explaining the improvements. "We've tightened the manufacturing tolerances," Parker said. "The British grenades show significant variation from unit to unit. Our production standards eliminate that variation. Every American grenade will perform identically." Crozier nodded but looked skeptical. "The British have thrown these things by the millions," he said. "They work. Our boys are going to France in weeks. They need grenades that work, not grenades that are precisely manufactured." What Parker couldn't explain, what American ordnance engineers wouldn't understand until American soldiers started dying in France, was that the variations in British grenades weren't manufacturing defects. They were deliberate features that made grenades more reliable under combat conditions. The improvements American engineers had made actually made the grenades worse. The fundamental mistake was treating grenade design as purely an engineering problem rather than an operational problem solved through brutal trial and error. British had developed their grenade design through experience. Soldiers threw grenades. Some worked perfectly, some failed. British engineers studied the failures, modified designs, and tested again. After thousands of iterations under combat conditions, they'd created a grenade that worked reliably in the chaos of trench warfare. American engineers received technical drawings of the final British design. They saw what appeared to be crude manufacturing and loose tolerances. They assumed British industry couldn't achieve precision, and the tighter tolerances would improve performance. They were wrong. The loose tolerances existed because combat experience had proven that precision grenades failed more frequently than variable grenades. Mud, dirt, moisture, rough handling, and stress of combat meant that grenades needed to be robust rather than precise. Over the next 18 months, from May 1917 through November 1918, American forces in France would discover this truth the hard way. American grenades manufactured to higher standards than British equivalents would fail at higher rates. American soldiers would die throwing grenades that didn't detonate or detonated prematurely. American casualties would mount because ordnance engineers in America had improved a design that didn't need improvement. The story of America's grenade development reveals fundamental lessons about technology transfer, the difference between theoretical engineering and practical design, and why copying something without understanding why it works the way it does leads to failure. It demonstrates that crude doesn't mean bad and precise doesn't mean better. And it shows how even close allies sharing technology freely can misunderstand each other when engineering culture and operational experience differ fundamentally. The British Genesis, Learning Through Dying. To understand why American improvements to British grenade design failed requires understanding how British grenades developed in the first place. British grenade design wasn't the product of careful engineering by ordnance experts. It was desperate improvisation by soldiers who needed weapons that didn't exist and couldn't wait for official development. When World War I began in August 1914, British forces had essentially no effective grenades. The Army's official grenade was a Victorian-era design that was dangerous to the thrower and ineffective against enemies. German forces, by contrast, had excellent stick grenades that could be thrown farther and exploded reliably. In early trench fighting, Germans could attack British positions with grenades, while British soldiers had no comparable weapons. British soldiers improvised desperately. They filled tin cans with explosives and added fuses. They created bombs from pipes and metal tubes. They invented the jam tin bomb, literally a jam can filled with gun cotton and shrapnel. These improvised weapons were crude and dangerous. They often failed to explode. They sometimes exploded prematurely, killing the thrower, but they were better than nothing. The Mills bomb, designed by William Mills and adopted in May 1915, represented the first standardized British hand grenade. Mills wasn't a military engineer. He was a businessman who'd manufactured golf clubs and automobile parts. He approached grenade design from practical rather than theoretical perspective. His grenade needed to be simple enough for mass production, reliable enough that soldiers would trust it, effective enough to kill enemies in trenches. The design Mills created looked crude to trained engineers. The body was cast iron, with grooves creating segments. The idea was that the segments would fragment on explosion, creating shrapnel. In reality, cast iron fragments randomly, regardless of grooves. The pineapple shape was partly decorative, partly to provide grip for throwing. The 4-second fuse was ignited by a spring-loaded striker released when the safety lever was released. But the Mills bomb worked. Soldiers could throw it accurately. It exploded reliably. The fragments killed or wounded enemies in a reasonable radius. Most importantly, it was safe to handle until the soldier deliberately released the safety lever. Previous British grenades had been so dangerous that soldiers feared them more than enemies. The Mills bomb was trusted. The key to the Mills bomb's success wasn't precision engineering. It was robust simplicity combined with extensive field testing. The design went through multiple iterations based on combat experience. Fuse timing was adjusted after soldiers reported premature detonations. The striker mechanism was simplified after complex versions failed in muddy conditions. The body design changed to improve fragmentation patterns. By 1917, when America entered the war, British had manufactured millions of Mills bombs. The design had been proven in every possible combat condition: mud, rain, snow, extreme heat, extreme cold, rough handling, storage in damp dugouts. The grenades worked. British soldiers trusted them completely. The design looked crude to engineers, but it was actually highly refined through trial and error under conditions no laboratory could replicate. The variations in British manufacturing that American engineers would later criticize as poor quality control were actually features. British grenades showed variation in fuse timing from 3.5 to 4.5 seconds. American engineers thought this variation was a defect. British soldiers knew it was a safety feature. If every grenade detonated at exactly 4 seconds, enemies could catch grenades and throw them back. Variable timing made that impossible. Enemies never knew if they had 1 second or 4 seconds, so they dove for cover instead of throwing back. Similarly, the cast iron body showed variation in fragmentation patterns. American engineers thought consistent fragmentation required precise manufacturing. British experience showed that variable fragmentation was actually more effective. Predictable fragment patterns meant enemies could find safe positions. Variable patterns meant no position was reliably safe. The Mills bomb represented the endpoint of evolution through combat. It wasn't designed theoretically and tested in combat. It was designed in combat through thousands of iterations where failure meant soldiers died. By 1917, the design had been optimized for actual combat conditions in ways no theoretical engineering could achieve. The crude appearance masked sophisticated practical design. April 1917, America's entry. When America declared war on Germany in April 1917, The United States Army faced immediate equipment crisis. American forces needed weapons quickly: rifles, machine guns, artillery, grenades, everything required for modern warfare. American industry had capacity to produce weapons, but needed designs immediately. The British and French offered their designs freely. They developed weapons through years of combat. American forces could adopt Allied weapons, produce them in America, and deploy to France equipped with proven equipment. This approach would get American soldiers into combat quickly with reliable weapons. American military leadership hesitated. Using foreign designs seemed to admit American engineering inferiority. American ordnance officers believed American engineers could improve Allied designs. The attitude reflected broader American confidence. American industry was the world's most productive. American engineers were highly skilled. American manufacturing standards exceeded European equivalents. Surely American versions of Allied weapons would be superior. For grenades specifically, American ordnance studied British Mills bombs, French F-1 grenades, and various other Allied designs. They analyzed construction methods, they tested samples, they evaluated manufacturing requirements. Their conclusion was that British Mills bomb was the best basic design, but needed improvements for American production. The decision to manufacture improved Mills bombs rather than exact copies reflected several assumptions. First, American ordnance believed tighter manufacturing tolerances would improve reliability. Second, they believed American detonator technology was superior to British equivalents. Third, they believed standardization across all grenades would simplify training and logistics. Captain James Parker, assigned to oversee grenade development, embodied American ordnance's approach. Parker was 32 years old, West Point graduate, trained in mechanical engineering. He'd never been in combat. His experience was theoretical knowledge and laboratory testing. He understood explosive physics, detonator mechanics, and manufacturing processes. What he didn't understand was how grenades actually worked in combat conditions. Parker studied British Mills bombs and immediately identified what he considered problems. The fuse timing varied too much. The striker mechanism was unnecessarily complex. The safety lever design was crude. The fragmentation pattern was unpredictable. Each of these represented opportunity for improvement through American engineering excellence. Parker's team designed what they called the Mark I grenade. It looked nearly identical to the Mills bomb externally: the pineapple body, the segmented design, the similar weight and size. But internally everything was improved. The fuse was manufactured to much tighter tolerances, ensuring consistent 4-second timing. The striker mechanism was simplified using better materials. The safety lever was redesigned for easier production. Even the explosive fill was modified to produce more consistent fragmentation. Production began in June 1917. American factories, tooled up to produce grenades, manufactured Mark I's by the thousands. The quality control was excellent by any manufacturing standard. Variation from unit to unit was minimal. Each grenade met specifications precisely. By every measurable standard, the Mark I was superior to the British Mills bomb it was based on. But there was a problem nobody recognized until American soldiers started using the grenades in combat. The improvements Parker's team had made actually reduced reliability under combat conditions. The precise fuse timing that seemed better in testing was worse in combat. The simplified striker that worked perfectly in clean conditions jammed in muddy trenches. The redesigned safety lever that was easier to manufacture was harder to operate with cold or wet hands. The Mark I grenade was a better grenade theoretically, but it was a worse grenade practically. The difference would cost American lives. Summer 1917, production and training. Through summer 1917, American factories produced Mark I grenades in enormous quantities. The manufacturing was impressive. American industry's efficiency and quality control were on full display. Factories in Pennsylvania, Ohio, and Massachusetts turned out grenades meeting specifications with variation measured in fractions of millimeters. Training began at American bases using the new grenades. Instructors taught proper throwing technique. Soldiers practiced with dummy grenades. Live fire exercises allowed soldiers to throw actual Mark Is and observe explosions. Everything seemed successful. The grenades worked perfectly under training conditions. The training environment, however, was nothing like combat conditions. Training occurred in good weather on prepared grounds. Grenades were stored in clean, dry magazines. Soldiers had time to prepare properly. They threw from stable positions at stationary targets. Under these ideal conditions, Mark I grenades performed flawlessly. Some training officers who had served with British forces expressed concerns. The Mark Is seemed more temperamental than British Mills bombs. They needed to be kept cleaner. The safety mechanism sometimes stuck if the grenade had been handled roughly. But these observations were dismissed. American manufacturing was superior. Any problems were attributed to user error or insufficient training. British liaison officers working with American forces preparing for France tried to warn about potential issues. British combat experience suggested the Mark I's tight tolerances might cause problems in muddy trenches. The precise fuse timing might actually be dangerous if enemies learned the timing was consistent. The simplified striker might jam under field conditions. American ordnance officers listened politely and disagreed politely. British concerns were appreciated but reflected British manufacturing limitations rather than design principles. American production standards would ensure reliability that British grenades couldn't match. The liaison officers dropped the subject, knowing that Americans would learn through experience just as British had. By September 1917, first American combat units were arriving in France. They brought with them thousands of Mark I grenades. American soldiers were confident in their equipment. Training had shown the grenades worked well. Instructors had emphasized that American manufacturing quality meant American grenades were more reliable than British equivalents. October 1917, 1st Combat used the 1st Division, 1st American Unit to enter combat operations, began aggressive patrolling in October 1917. These patrols allowed American soldiers to gain combat experience before major operations. Patrols also allowed testing of American equipment under actual combat conditions. The first combat use of Mark I grenades occurred during a trench raid on October the 23rd. A patrol from the 16th Infantry Regiment attacked a German position. The plan called for grenades to suppress German defenders while American soldiers closed for assault. 8 soldiers carried Mark Is for the operation. The raid began at 0200 hours. American soldiers approached German trenches undetected. At signal, they threw their grenades. 2 grenades exploded perfectly. 3 failed to detonate at all. 2 detonated prematurely while still in mid-throw, wounding the throwers. 1 grenade safety lever stuck, and the frustrated soldier had to discard it without throwing. The raid became a disaster. The grenades that failed to explode alerted Germans without suppressing them. The premature detonations wounded American soldiers and revealed the attack. German defenders, now alert and unharmed, opened fire. The American patrol withdrew with 3 dead and 5 wounded. 2 of the dead had been killed by their own premature grenades. The after-action report noted grenade malfunctions, but attributed them to user error or combat stress. Perhaps soldiers hadn't released safety levers properly. Perhaps they'd held grenades too long before throwing. The possibility that the grenades themselves were flawed wasn't seriously considered. But more reports came in, different units, different sectors, same problems. Mark I grenades failing at alarming rates. Some didn't explode, some exploded too quickly, some safety mechanisms stuck. American soldiers began losing confidence in their grenades. Worse, they began requesting British Mills bombs to replace their American grenades. By November 1917, the problem was undeniable. Statistical analysis showed Mark I failure rates around 15%. British Mills bombs showed failure rates around 3% under same conditions. American grenades were failing 5 times more frequently than British grenades they were supposed to improve. If you're shocked by how American over-engineering made a simple weapon worse, hit that subscribe button right now. We're about to explore the specific technical mistakes American engineers made and how British soldiers tried to help fix problems that shouldn't have existed. Don't miss what comes next. The technical failures when precision makes things worse. Understanding why Mark I grenades failed requires examining specific design changes American engineers made and why those changes caused problems under combat conditions. The fuse timing problem was the most dangerous failure. American engineers had tightened manufacturing tolerances to ensure consistent 4-second fuses. Every Mark I was supposed to detonate exactly 4 seconds after the striker ignited the fuse. In testing, this consistency seemed ideal. In combat, it was deadly. The problem was that German soldiers quickly learned American grenades had consistent timing. When Americans threw grenades, Germans would watch them land and count. 1, 2, 3. Dive for cover. 4. Explosion. The predictable timing allowed Germans to minimize exposure. With British Mills bombs, Germans never knew if they had 1 second or 5 seconds, so they dove for cover immediately. Worse, the consistent timing created a danger American soldiers hadn't anticipated. If a soldier accidentally struck the grenade against something while pulling it from their belt, the striker might fire without the soldier realizing it. With variable British fuses, the soldier might have 3 to 4 seconds to notice and throw. With precise American fuses, the soldier had exactly 4 seconds. Several American soldiers died because they didn't notice their grenade was armed and exploded before they could react. British fuses deliberately varied from 3.5 to 4.5 seconds. This variation was built into the manufacturing process intentionally. British engineers had learned through bitter experience that variable timing was safer for users and more effective against enemies. American engineers, not understanding this operational logic, had eliminated variation as a defect. The striker mechanism problem was equally serious. American engineers had simplified the British striker mechanism, removing what they considered unnecessary components. The American striker used fewer parts, was easier to manufacture, and worked perfectly in clean conditions. But in muddy trenches, the simplified mechanism jammed frequently. British striker mechanism had more parts but included redundancy. If one component became dirty or damaged, others compensated. The mechanism was designed to work even when caked with mud, frozen by cold, or rusted by moisture. American mechanism was designed for optimal performance under ideal conditions. Combat conditions were never ideal. The result was that American grenades often failed to detonate when thrown. The striker mechanism jammed, preventing fuse ignition. British soldiers could pull grenades from muddy pouches, wipe them on their pants, and throw them confidently. American soldiers needed to carefully clean their grenades before use or risk failure. In combat, careful cleaning wasn't always possible. The safety lever problem affected usability rather than reliability, but was equally frustrating. American engineers had redesigned the British safety lever to reduce manufacturing complexity. The American lever required less precise bending and forming, making production easier. But the redesign made the lever harder to grip and release, especially with wet or cold hands. British soldiers wore fingerless gloves in winter, allowing them to maintain dexterity while keeping hands warm. They could grip and release the British safety lever even with gloved hands. American safety lever required more finger strength and finer motor control. American soldiers often couldn't release the lever properly with gloved hands. They had to remove gloves, exposing hands to cold and injury. The explosive fill modification proved less problematic, but still represented misunderstanding. American engineers had modified the explosive composition to produce more consistent fragmentation. They'd calculated theoretically optimal fragment size and modified the explosive to achieve it. The result was fragments that were very consistent in size, but not necessarily more lethal. British had learned that variable fragment sizes were more effective than consistent sizes. Large fragments caused severe wounds. Small fragments caused multiple minor wounds that degraded combat effectiveness. The mixture of sizes was more effective than optimized uniformity. American optimization had made the grenade less effective while making manufacturing more complicated. Each of these problems shared the same root cause. American engineers had optimized grenades for measurable performance under ideal conditions. British engineers had optimized grenades for adequate performance under worst possible conditions. Combat conditions were never ideal. They were always worst possible. British crude designs worked in chaos. American precise designs worked in laboratories. December 1917 through March 1918. The resistance. By December 1917, American combat units were refusing to use Mark I grenades when alternatives were available. Units training with British forces requested Mills bombs. Units in quiet sectors hoarded captured German stick grenades. Anything was preferable to American grenades that failed too frequently. American ordnance officers receiving reports of grenade failures initially resisted acknowledging problems. The reports were attributed to improper training, user error, or combat stress. Statistical analyses showing 15% failure rates were questioned. Perhaps American soldiers were handling grenades roughly. Perhaps they weren't following proper procedures. British liaison officers tried to help. They arranged demonstrations where British and American soldiers threw both types of grenades under similar conditions. The differences were obvious. British Mills bombs worked reliably even when thrown by soldiers who'd pulled them from mud, hadn't cleaned them, and threw them immediately. American Mark I's required careful handling and often failed under same conditions. These demonstrations were conducted at battalion and regimental levels repeatedly through winter 1917-18. Each time results favored British grenades. Each time American ordnance representatives observed and took notes. Each time official reports minimized problems and attributed differences to factors other than design flaws. The resistance to acknowledging problems reflected institutional factors. Admitting American grenades were inferior to British equivalents meant admitting American engineering had failed. It meant halting production of tens of thousands of grenades already manufactured. It meant the embarrassment of requesting British grenades to replace American ones. None of these options appealed to American military leadership or ordnance establishment. Captain Parker, whose team had designed the Mark I, was particularly defensive. He'd followed proper engineering principles. He'd improved British design using American manufacturing capabilities. The problems had to be user error or insufficient training. He resisted suggestions that design changes were needed, but pressure mounted from combat units. Regimental commanders reported that soldiers lacked confidence in American grenades. Battalion commanders requested permission to use British grenades exclusively. Company commanders reported that soldiers were voluntarily carrying fewer grenades because they didn't trust them. The grenade was becoming more dangerous to American soldiers than to German enemies. In January 1918, General John Pershing, commanding American Expeditionary Forces, ordered a comprehensive evaluation. British and American grenades would be tested under controlled conditions, supervised by officers from both armies. The results would determine whether modifications to American grenades were necessary. The testing occurred in February 1918 under conditions designed to simulate combat. Grenades were stored in damp conditions. They were covered with mud. They were frozen. They were dropped and roughly handled. They were thrown by soldiers wearing gloves. Every test replicated actual combat conditions as closely as possible without actual combat. British Mills bombs passed essentially every test. Failure rate under all conditions remained below 5%. Most failures were fuses that burned too quickly or too slowly rather than complete failures to detonate. Even when caked with mud or frozen solid, most British grenades worked. American Mark I's failed dramatically. Failure rates exceeded 20% under adverse conditions. Striker mechanisms jammed, safety levers stuck, fuses failed to ignite. Under conditions similar to actual combat, American grenades were essentially unreliable. The test results were undeniable. American ordnance could no longer dismiss complaints as user error. The Mark I grenade was fundamentally flawed for combat conditions. Modifications were necessary immediately. March through July 1918, the redesign. In March 1918, American ordnance finally acknowledged that Mark I grenades needed redesign. Captain Parker's team was expanded with officers who had combat experience. British engineers were invited to consult directly. The goal was to modify American grenades to achieve British reliability while maintaining American manufacturing standards. The redesign process revealed how difficult it was to add robustness to a design optimized for precision. Every modification that improved reliability under adverse conditions reduced manufacturing precision. Every attempt to maintain precision degraded reliability. The two goals were fundamentally opposed. The fuse timing modification was simplest. American engineers added deliberate variation to fuse manufacturing. Instead of trying to achieve exactly 4 seconds every time, they manufactured fuses ranging from 3.5 to 4.5 seconds intentionally. This required relaxing quality control standards, which went against every instinct of American manufacturing culture. But it worked. Variable timing made grenades safer to use and more effective against enemies. The striker mechanism proved more difficult. Adding redundancy meant adding complexity. Adding parts meant more manufacturing steps. American engineers wanted to maintain simple American design while adding British reliability. This proved impossible. Eventually, they adopted British striker mechanism, essentially unchanged, acknowledging that British design was actually superior despite appearing more complex. The safety lever was redesigned completely. American engineers swallowed their pride and copied British lever design exactly. The British design was harder to manufacture precisely, but easier to operate under combat conditions. Function mattered more than manufacturing elegance. The explosive fill modification was reversed. American engineers abandoned their optimized fragmentation approach and returned to British explosive composition. Variable fragment sizes proved more effective than consistent sizes, regardless of theoretical calculations. By May 1918, the redesigned grenade, designated Mark I Modified or Mark I-A, was ready for testing. It looked identical to original Mark I externally. Internally, it was essentially a British Mills bomb manufactured to slightly tighter American tolerances, where those tolerances didn't affect reliability. Testing in June 1918 showed dramatic improvement. Failure rates under adverse conditions dropped below 5%, matching British performance. American soldiers testing the new grenades reported confidence in them. Combat trials in July showed they worked reliably under actual conditions. Production of Mark I-A began in August 1918. Factories that had been producing original Mark I's converted to the modified design. The conversion required significant retooling. Manufacturing standards had to be deliberately relaxed in specific ways. Quality control had to accept variation that would have been rejected previously. The modified grenades began reaching American units in France in September 1918. Soldiers who'd refused to carry original Mark I's accepted Mark I grenades willingly. Combat reports showed the new grenades worked as reliably as British Mills bombs. The failure rate dropped to acceptable levels. The cost, lives, and lessons. The delay in fielding reliable American grenades had measurable costs. From October 1917, when American units first used Mark I's in combat, through September 1918, when reliable Mark I-A grenades finally deployed, American forces operated with grenades that failed too frequently. Statistical analysis of casualty reports suggests approximately 200 American soldiers died directly from Mark I grenade failures. Some were killed by premature detonations. Some died when grenades failed to suppress enemy positions. Some were wounded by malfunctioning grenades that exploded unexpectedly. Each death was attributable to design flaws that British experience could have prevented. The indirect costs were higher. Units lacking confidence in their grenades were less effective in close combat. Attacks that should have succeeded failed because grenades didn't work. Patrols that should have been routine became dangerous because soldiers couldn't rely on their weapons. The cumulative effect degraded American combat effectiveness during critical months of 1918. The waste of resources was enormous. Tens of thousands of original Mark I grenades had been manufactured and shipped to France. These grenades were withdrawn from service and eventually destroyed. The manufacturing capacity consumed producing defective grenades could have produced other needed equipment. The shipping space used transporting defective grenades could have carried useful supplies. Most significantly, American military prestige suffered. British and French allies who'd offered to supply proven weapons saw Americans insist on manufacturing supposedly superior versions only to field inferior equipment. German intelligence learned that American grenades were unreliable and adjusted tactics accordingly. The perception that American weapons were flawed affected Allied confidence in American forces. The lessons were painful but clear. First, copying technology without understanding operational context leads to failure. American engineers had technical specifications for British grenades, but not operational experience explaining why specifications were what they were. The variations and apparent imprecision in British designs were actually refined features, not manufacturing defects. Second, theoretical optimization often makes practical performance worse. American engineers optimized grenades for measurable performance under ideal conditions. British engineers optimized for adequate performance under worst possible conditions. Combat conditions were never ideal. Optimization for ideal conditions guaranteed failure in reality. Third, manufacturing precision doesn't equal weapon reliability. American manufacturing standards emphasized consistency and tight tolerances. British manufacturing accepted variation and loose tolerances where appropriate. Precision manufacturing produced grenades that worked perfectly in clean conditions but failed in dirt. Variable manufacturing produced grenades that worked adequately always. Fourth, experience matters more than theory. British grenade design reflected thousands of combat iterations. American grenade design reflected theoretical engineering. Theory without experience produced failures. Experience without theory produced success. The combination of British operational knowledge with American manufacturing capability eventually produced excellent results, but only after American engineers learned to respect experience over theory. Before we wrap up this story of how overconfidence led to failure, I want to ask one more time. If you're fascinated by these lessons about engineering hubris and the cost of not listening to experience, hit that subscribe button. We've got one final section about the lasting impact and why these lessons still matter in modern military development. Don't miss the conclusion. Post-war analysis. What went wrong and why? After the war ended in November 1918, American military conducted comprehensive review of equipment performance. The grenade failures were examined in detail. The analysis revealed patterns that extended beyond grenades to broader questions about American military development. The fundamental problem was cultural. American engineering culture emphasized measurable improvement through systematic analysis. When presented with foreign technology, American engineers instinctively looked for ways to improve it. The assumption was that American engineering excellence could optimize any design. This assumption was sometimes correct, but often wrong. British engineering culture, particularly for military equipment developed under wartime pressure, emphasized adequacy under worst conditions over optimality under ideal conditions. British engineers designed for Murphy's Law. Whatever could go wrong would go wrong under combat conditions. Equipment had to work despite problems, not because problems were prevented. These different philosophies produced different designs. American designs were elegant, precise, and optimal under controlled conditions. British designs were crude, variable, and adequate under chaotic conditions. In laboratories, American designs usually outperformed British equivalents. In combat, British designs usually worked better. The grenade case study demonstrated this pattern clearly. American Mark I was objectively superior to British Mills bomb by every measurable laboratory standard. Tighter tolerances, more consistent performance, better quality control. But in combat, it failed more frequently because combat wasn't a laboratory. American ordnance officers struggled to understand this initially because their training emphasized theoretical knowledge over operational experience. Captain Parker and engineers like him had excellent educations. They understood explosive physics, mechanical engineering, and manufacturing processes. What they lacked was experience with equipment failure under combat stress. British engineers had that experience because they developed equipment while fighting for survival. The resistance to acknowledging problems reflected institutional factors. Admitting American grenades were inferior meant admitting American engineering had failed. It challenged assumptions about American industrial and technical superiority. It required acknowledging that Allied equipment developed under wartime pressure might be better than American equipment developed systematically. This resistance delayed solutions by months. If American ordnance had immediately accepted British advice in October 1917, the Mark I could have been corrected by December. Instead, American engineers spent months proving to themselves what British engineers already knew. The delay cost lives. The lesson about listening to operational experience proved valuable beyond grenades. American forces developing other equipment began including combat veterans and Allied liaison officers early in design processes. The systematic exclusion of operational experience from engineering processes was recognized as fundamental flaw. Modern military development has institutionalized this lesson. American weapon development now includes extensive operational testing under realistic conditions before production decisions. The tradition of allowing engineers to optimize designs without operational input has been replaced by integrated teams including engineers, operators, and combat veterans. The legacy: Mills bombs and modern lessons. The Mills bomb itself had remarkable legacy. British continued using Mills bombs through World War II. The design proven in World War I trenches remained effective in World War II combat. The hand grenade's basic requirements, portable explosive that can be thrown accurately and detonates reliably, didn't change much between wars. American forces in World War II used grenades descended from the corrected Mark I-A rather than original Mark I. The World War II. Mark II grenade incorporated British operational lessons learned painfully in World War I. American engineers designing Mark II included combat veterans who understood that reliability mattered more than precision. The broader lessons about technology transfer remain relevant. Modern militaries frequently acquire foreign technology through purchase, license, or alliance cooperation. The temptation to improve foreign designs before deployment remains strong. American engineering culture still emphasizes optimization and improvement, but modern acquisition processes have learned World War I lessons. When acquiring foreign technology, American military now seeks operational experience and doctrine along with technical specifications. Why does the original design work the way it does? What operational conditions shape development? What failures led to current configuration? These questions are asked systematically. The grenade story also illustrates challenges of technology transfer to developing nations. Countries acquiring advanced Western military equipment often focus on technical specifications while missing operational doctrine and support requirements. Equipment fails not because technology is inadequate, but because operational context differs from original development environment. Commercial technology transfer faces similar issues. Companies licensing foreign technology sometimes fail because they copy product without copying operational philosophy. Japanese success in licensing American technology in post-war decades succeeded partly because Japanese companies sought to understand not just what American products did, but why they worked as they did. The specific lesson about precision versus robustness remains relevant across engineering fields. Modern consumer electronics face similar trade-offs. Products optimized for ideal conditions often fail in actual use. Smartphones that work perfectly in controlled environments but fail when dropped, exposed to moisture, or subjected to temperature extremes reflect same mistake American ordnance made with grenades. Military equipment development still struggles with laboratory versus field performance. Equipment tested extensively under controlled conditions sometimes fails in combat because combat conditions were inadequately simulated. The challenge of testing equipment under realistic conditions while maintaining safety and controlling costs remains unresolved. Conclusion: the grenade that taught humility. The story of America copying Britain's Mills bomb grenade and making it worse is ultimately a story about humility. American engineers in 1917 were confident that American methods could improve any design. British grenades appeared crude and imprecise. American engineering would optimize them. But combat revealed truth that laboratories couldn't. British grenades, developed through brutal operational experience, were refined practical designs that worked reliably under worst possible conditions. American grenades, developed through systematic engineering, were optimized for ideal conditions that never existed in combat. The cost of this lesson was approximately 200 American lives lost directly to grenade failures, plus countless more lost indirectly through reduced combat effectiveness. The cost in wasted resources, delayed deployment of reliable grenades, and damaged prestige was substantial. The cost in learning that engineering excellence without operational experience leads to failure was invaluable. American ordnance eventually got it right. The Mark I-A grenade, incorporating British operational lessons, worked reliably. But the path from arrogant improvement to humble correction took nearly a year and cost lives. The lesson about respecting operational experience over theoretical optimization remains relevant. The British Mills bomb worked because it was developed by people who needed it to work to survive. Every failure meant British soldiers died. Every problem was corrected through experience. By 1917, the design had been refined through millions of throws under every possible condition. It wasn't elegant, but it was effective. The American Mark I failed because it was developed by people who wanted it to be better without understanding what better meant. Every optimization made sense theoretically. Every improvement seemed logical. But the optimizations and improvements were for conditions that didn't match combat reality. Theoretical better was practically worse. Why did America copy Britain's improvised grenade and still get it wrong? Because Americans treated grenade design as engineering problem to be solved through systematic optimization. British treated grenade design as survival problem to be solved through whatever worked. Engineering without operational experience produced elegant failures. Experience without theoretical optimization produced crude success. The story teaches that technology transfer requires transferring not just specifications, but philosophy. That copying something without understanding why it works that way leads to failure. That crude doesn't mean bad and precise doesn't mean better. That combat conditions never match laboratory conditions. That soldiers' lives depend on equipment that works always, not equipment that works perfectly sometimes. The Mills bomb worked in trenches, in rain, in mud, in cold. After rough handling with minimal maintenance, it worked because British engineers had learned through deaths what worked and what didn't. American engineers tried to improve it without that experience. They made it work better in laboratories and worse in combat. Eventually they learned, but learning cost lives. The Mark I grenade that finally worked was essentially a British Mills bomb with slightly better American manufacturing where that manufacturing didn't interfere with operational reliability. It was American admission that British engineers had been right. That operational experience mattered more than theoretical knowledge. That crude designs proven in combat were better than elegant designs proven in laboratories. Today's military equipment development incorporates these lessons. Operational experience drives design. Combat veterans participate in engineering. Field testing under realistic conditions precedes production decisions. The systematic exclusion of operational input that characterized World War I American ordnance no longer exists. The price of learning was high, but the lesson was learned. The British Mills bomb remained in service through 2 world wars and beyond. The design proven in World War I trenches worked in World War II combat, in Korea, and in countless other conflicts. Simple, robust, reliable. Everything a hand grenade needed to be, everything American engineers initially failed to understand. They gave us the design. We improved it and made it worse. We refused to believe it was worse. Combat proved we were wrong. Eventually, we admitted it. Eventually, we fixed it. Eventually, we got it right. The path from arrogant improvement to humble correction is the story of American grenade development in World War I. The lesson remains. When copying technology developed through operational experience, respect that experience. Don't assume you can improve it through pure engineering. Understand why it works before trying to make it better. And remember that better in theory often means worse in practice. The soldiers who depend on your equipment will pay the price of your assumptions. Make sure your assumptions are correct before soldiers start dying to prove them wrong.